Hey HMS modelers, this is Mike Bartles from the Hydrologic Engineering Center. In this video, we'll finish up talking about loss methods within HEC-HMS for now by discussing the green-ampt method. By the end of this video, you should be familiar with the green-ampt method. We'll look at an example computation, discuss some common data sources, parameter estimation techniques, and calibration techniques. And at the end, we'll finish up by comparing advantages and disadvantages of this method. All right, let's get going. The green-ampt infiltration equation is more physically based than the previously discussed options. This method was first proposed in 1911 by two guys named Green and Ampt, as the name implies. I'll spare you guys the gory mathematical details, but within this method, infiltration proceeds with so-called piston displacement, as shown in the figure in the bottom right. Now remember, infiltration in the real world, as shown in the bottom left figure. The Green and Ampt method tracks the downward movement of water, but it doesn't allow for heterogeneities to outpace the bulk of infiltrated water. Everything proceeds downward in a uniform front, and this wetting front, as it's called, is a sharp boundary dividing the saturated portion of the soil from the unsaturated portion. The total amount of infiltration is equal to the depth of infiltrated water times the change in soil moisture from initial conditions to saturation. Now, while this method doesn't allow for evapotranspiration, there is a layered green and ampt option also within HEC-HMS that does allow for evapotranspiration to be included. Remember the figure on the left from previous videos? The initial and constant and deficit and constant infiltration methods could only approximate the exponential decrease in infiltration rate with blocky rectangles of initial loss and constant loss. However, the green and ampt method can recreate that exponential decrease and eventual asymptotic limit at the saturated hydraulic conductivity. Now compare the two images. They look pretty similar, right? That's what Green and Ampt set out to do when they devised this method in 1911. Now, in using this method, you're required to specify either 4 or 5 parameters, depending upon the choice of initial condition. In this example computation, a subbation shown using the parameters in the left is subjected to a constant precipitation rate of 1 inch. In the table to the right, notice that the loss rate is initially high, but decreases exponentially towards the specified saturated hydraulic conductivity of 0.2 inches per hour. And it doesn't quite reach that limit in this example, but given more precipitation and more rows in this table, it would get closer and closer. Now let's talk about parameter estimation for this method. You must specify the initial condition in one of two ways, as an initial content or as an initial deficit. In either case, the initial condition must be specified in terms of a volume ratio, like cubic inch per cubic inch. The initial condition should be estimated like it was for initial and constant and deficit and constant. Scrutinize the prevailing antecedent conditions prior to the start of your simulation. But this should then be related to the saturated content, as I'll talk about on the next slide. The saturated content parameter must be specified when using the initial content method. However, when using the initial deficit method, you'll still need to know what this is to actually calculate an initial deficit. Now, this parameter refers to the maximum water holding capacity of the soil, and usually the soil's effective porosity is a good place to start with this parameter. Similar to the initial content or initial deficit, this parameter must be specified as a volume ratio, like cubic inch per cubic inch. Like most other infiltration parameters, I like to estimate the saturated content of a soil by relating the superficial texture from a soil's database to published literature values. The wetting front suction head describes how infiltrated water moves downwards through the soil column. It's essentially the force that is exerted on infiltrated water by the soil that acts in the downward direction. This parameter must be specified as an effective depth, like inches or millimeters. I also like to estimate this parameter by first extracting superficial textures from the soil's database and then relating them to published values for the predominant soils. Now recall that a soil's saturated hydraulic conductivity refers to the minimum rate at which precipitation will be infiltrated after the soil is fully saturated. This parameter can also be estimated by first extracting superficial textures from the soil's database and then relating them to published saturated hydraulic conductivity values for the predominant soils. And finally, like I've said in previous videos, the percent impervious area can be estimated using a GIS source like the National Land Cover Database. But be sure to include large standing water bodies in these estimates, as rain falling directly onto a large lake or reservoir should not be subject to infiltration. Like I talked about in previous videos, I like to calibrate my infiltration parameters by first modifying the initial estimates until I get the initiation of runoff correct, then attempt to match the observed runoff volume. In this example here, observed flow is shown in black and computed flow is shown in blue. The initiation of runoff looks good, but my peak is off. So I need to decrease my saturated hydraulic conductivity to allow for more runoff and less infiltration. Make sure you use multiple statistical metrics when you calibrate, like Nash cyclic efficiency and percent bias, to measure model performance. Now let's finish by talking about advantages and disadvantages to this method. The primary advantages when using the green-ampt method are that all the parameters can be related to predominant soil textures, and predicted infiltration is in accordance with classical unsaturated flow theory. And this means that it's a good choice when you don't have observed runoff data. However, this method is more complicated than either the initial and constant and deficit and constant methods. Because of that, it hasn't been applied as many times as initial and constant or deficit and constant. Also, since it has more parameters, this method is less parsimonious than simpler methods. Now to recap, in this video, I introduced the green-ampt infiltration method, which recreates observed infiltration phenomena like an exponential decrease in infiltration rate and an asymptotic limit. Now, the parameters required by this method can all be related to predominant soil textures. This makes the green-ampt method a great option for applications with little to no observed runoff data. However, this method is more complex and requires more inputs than simpler methods like initial and constant and deficit and constant. But all in all, it's a great method to use once you become familiar with it. Now, thanks for watching these loss method videos. I'll see you in the future to discuss additional modeling topics.